Alright, so we'll begin with the basic concepts behind induction motors. Now, from our basic theory of machinery principles, we know that if we have a three-phase set of voltages, and of course the voltages will be 120 degrees out of phase one to the next, and we apply this to the stator of an induction motor, or in general if we apply it to a three-phase set of windings which are located 120 degrees from each other, then we will get a three-phase set of currents which will give rise to a magnetic field which will rotate, and for the purpose of this analysis we're going to assume that it rotates in the counterclockwise direction. So a three-phase set of voltages applied to the stator of an induction motor this gives rise to a three-phase set of currents which then gives rise to a rotating magnetic field which we are going to call B sub S. And let's assume that it rotates in the counterclockwise direction. Okay, so the first question we would ask about B sub S is, what is the speed of its rotation? The speed of its rotation, which is called the synchronous speed, is equal to 120 times the electrical frequency, that is the frequency of the three-phase voltages, divided by P, where P is equal to the number of magnetic poles in the machine. Now, if we consider a squirrel cage type induction motor, and in the squirrel cage type induction motor we have two rings at either end of the rotor that are connected by a number of what are called rotor bars, which would be made generally from copper or aluminum conducting material. And if we think about one of these rotor bars and the induced voltage on that rotor bar, because of course we've got a moving magnetic field now, and we have a conductor, the rotor bar, inside that magnetic field, so we're going to get an induced voltage on the rotor bar, and we can write an expression for that. V cross B dot L. Here V is the relative velocity of the rotor bar to the magnetic field. B is the magnetic flux density vector. is the length of the bar, or the conductor, inside the magnetic field. Okay, so there's our induced voltage. And again, this induced voltage is produced because of the relative motion between the rotor and the stator magnetic fields. So let's make a quick drawing here. If we consider we've got a rotor inside a stator, and the rotor is rotating at omega m, and we've got these rotor bars. The velocity of the upper bars relative to the magnetic field is to the right. So the induced voltage, the polarity of the induced voltage is into the page. And the lower bars, here we consider that B sub s is in this direction. The velocity of the lower bars is out of the page because it is moving in the opposite direction. It's moving to the left relative to B sub s. So the result is that we get a current out of the upper bars and into the lower bars. And since the rotor is electrically inductive, the result is that the peak current in the rotor will lag the peak voltage. So here we have voltage into the page in the upper bars, and we have a voltage out of the page in the lower rotor bars. So we get a current out of the upper bars into the lower bars. So we have this current in the rotor. And again, we said that the rotor is inductive. And therefore the current is going to lag the voltage. So we have this current in the rotor, which gives rise to a rotor magnetic field, which we'll call B sub r. And so then we can talk about the vector sum of the two, B net, and we have an induced voltage E sub r and a current, and that current lags the voltage I sub r. So we think about the interaction between the stator magnetic field B sub s and the rotor magnetic field B sub r, and that interaction is going to create a torque. So we have an induced torque. And the induced torque will be equal to K, some constant, times the cross product of B sub R and B sub S. And in our example here, it would be in the counterclockwise direction. Okay, let's consider the situation where the rotor were turning at the synchronous speed. So, if the rotor, let's say was turning, or is turning at the synchronous speed, what would the situation be then? Well, if that were the case, then the rotor bars would be stationary relative to the magnetic field. And so we would have no relative motion between the conductors and the magnetic field, so the induced voltage would be zero. Okay, if the induced voltage is zero, then we would have no current in the rotor. And if the rotor current is zero, then the magnetic field in the rotor would be zero. B sub R is equal to zero. And if B sub R is equal to zero, then the torque is equal to zero. Because remember, the torque is the cross product between the rotor and stator magnetic fields. Rotor magnetic field goes to zero, torque goes to zero. As a result of this sequence of events, we can conclude that an induction motor can approach the synchronous speed, but it can't reach the synchronous speed. The reason it can't reach the synchronous speed is because there will always be some friction or losses to overcome. And at the synchronous speed, there would be no torque to overcome those losses, so it cannot reach that synchronous speed. This brings us to the concept of rotor slip. I'm going to define the slip speed and this slip speed is the difference between the synchronous speed and N sub m, which is the mechanical shaft speed or the motor speed. The speed at which the shaft is turning. Now we can define slip S for slip is equal to the synchronous speed minus the shaft speed divided by the synchronous speed, and we'll either express it as a decimal or as a percentage. we could rewrite these expressions using the angular speed in radians per second using omega, or here we're expressing it in revolutions per minute using n. The expressions would be exactly the same. So as a result of these equations, we can express the mechanical speed n sub m equal to 1 minus s, the slip, times the synchronous speed. If we were doing all this in radians per second, it would just be omega m 1 minus s omega sync. Okay. So if we think about what we've said about the induction motor so far, we've got a three-phase stator that we apply a three-phase set of voltages to, giving rise to a three-phase set of currents, just like in the primary side of a transformer. And then we induce a voltage on the secondary side, which gives rise to an induced current. And now we've been talking about the magnetic field associated with that induced current, B sub r. But this starts to sound a lot like a transformer. And in fact, it is a lot like a transformer, with really one critical difference. And that critical difference is that we have relative motion between the primary and the secondary sides. If you think of the primary side of a transformer as the stator, and the secondary side of the transformer as the rotor, then if we were to lock that rotor and fix its position, we would have a transformer. We would essentially have a transformer. But once we allow that rotor to turn, which is the normal mode of operation for an induction motor, we're going to have this relative motion between the stator and the rotor, or the primary and the secondary, if we're thinking in terms of the analogy to a transformer. And one of the key effects that this has is it changes the electrical frequency in the rotor. So that's what we're going to talk about now. Recall that in a transformer, the frequency on the primary side is equal to the frequency on the secondary side. But as we're going to see, that's not the case in the induction motor. So we said if the rotor were locked, it would have the same frequency as the stator. We would have the same situation as in the transformer. So that's sort of one extreme, the locked rotor extreme. The other extreme would be that if the rotor were moving at synchronous speed. And if that were the case, we've already said that the induced voltage would be zero, the current would be zero, and therefore the magnetic field in the rotor would be zero and the torque would be zero, but also the frequency would be zero. So between the locked rotor condition and the rotor turning at synchronous speed, we see that the frequency varies from whatever the frequency is on the stator, say 60 Hertz, down to 0. And in fact, the rotor frequency is directly proportional to the difference between the speed of the magnetic field, or the synchronous speed, and the speed of the rotor. So, since the slip is equal to the difference between the synchronous speed and the shaft speed divided by the synchronous speed. And here I'm going to leave the times 100% out. We're going to express it as a decimal. We can express the rotor frequency F sub r is equal to S times F sub B. So if we multiply the slip, whatever slip we're operating at, times the electrical frequency, that's the frequency that we'll get on the rotor. So that we see that as the mechanical speed gets higher, the frequency in the rotor is going to get smaller. We can expand this a bit. Since the synchronous speed is equal to 120 F sub E over P, the number of poles, we can write F sub R is equal to N sync minus Nm over N sync F sub E, which is equal to the difference between the synchronous speed and the shaft speed times P over 120 F sub E times F sub E. Here I've substituted in this expression for the synchronous speed expression in the denominator, and this is equal to P over 120 times the difference between the synchronous speed and the shaft speed. And we see that we can actually express the frequency in the rotor as an expression that doesn't have the stator frequency in it. It doesn't explicitly have the stator frequency. Okay, so we've talked about how an induction motor is a lot like a transformer, so it would stand to reason that the equivalent circuit of an induction motor should be similar to the equivalent circuit of a transformer. And that turns out to be the case, except for this one difference that we've talked about that we need to account for. So let's analyze and derive an equivalent circuit for an induction motor. So let's just start out with the transformer circuit model. Transformer circuit model, we have our primary side resistance and inductance, and then we have our excitation branch, which captures our core losses, as well as the inductive component in the core. And then we had an ideal transformer, and we have this voltage here, which we call E1, and we have A, the turns ratio. We're going to call it A effective, the effective turns ratio. And then we have the other side of the transformer. We'll call this voltage ER. And here we have an inductor, JXR, and we have a resistor, R sub R. So R1 is our stator resistance, X1 is the stator leakage resistance, the magnetization reactance X sub M. I'm sorry, the X1 is the stator leakage reactance, magnetization reactance XM, magnetization resistance R sub C. And if we were to compare the general shape of the magnetization curves of a transformer and an induction motor, we would see in general the following difference. If our transformer magnetization curve looked like this, of course passing through the origin, the induction motor may look more like this. So we see that the slope of the induction motor is shallower, and the reason, so this one is the induction motor. This one would be the transformer. So the reason the induction motor has a shallower slope is because we have to have an air gap in the induction motor in between the stator and the rotor, and this increases the reluctance of the flux path and reduces the coupling between the primary stator and secondary rotor windings. Okay, so it's just simply this air gap and the increased reluctance as a result of that air gap that gives us a shallower magnetization curve here. Whereas for the transformer, we can have the primary and the secondary windings basically wrapped right on top of one another, so we get better coupling between the primary and the secondary, and therefore we get a steeper magnetization curve. Now, the higher reluctance in the air gap means that we need more magnetization current in order to obtain a given flux level. So let's just make a note of some of these things. The shallower magnetization curve for the induction motor is due to let's say a higher reluctance because of the air gap between stator and rotor. And higher reluctance means more magnetization current. To obtain a given flux level. So if we look back at the circuit, the primary internal state voltage E1 is coupled to the secondary internal state voltage ER by this effective turns ratio A effective. And we say the effective turns ratio because if we're talking about a squirrel cage induction motor that doesn't have windings on the rotor, we can't really talk about a turns ratio because there are no turns on the rotor. It's just the rotor bars. So that's why we call it effective turns ratio. And the transformer model differs from the induction motor model because of the effects of the varying frequency on E sub r, and therefore on the rotor impedances R sub r and X sub r. So if we consider that the frequency of E sub r is a function of the speed of the motor and therefore the slip, we realize that our impedances, in particular Jx sub r, is going to become a function of the motor speed. And therefore it's not constant like it was in the transformer model. So the situation now is that we have a voltage, three-phase voltage applied to the stator windings of an induction motor, and this induces a voltage on the rotor. And in general, the greater relative motion between the rotor and the stator, the greater the resulting rotor voltage and frequency. The largest relative motion occurs in the situation we talked about before, where the rotor is stationary. And in this case, that's the locked rotor condition. And in this case, the frequency on the rotor is equal to the frequency in the stator. The other extreme condition that we talked about is when the rotor moves at the same speed as the stator magnetic field, or the synchronous speed, and in this case the rotor voltage is 0 and the frequency is 0. Okay, so we can think about the magnitude and frequency of the voltage induced on the rotor being directly proportional to the slip of the motor. That is, E sub r is equal to S times E sub r naught, where E sub r naught is equal to the magnitude of the induced rotor voltage at the locked rotor condition. When we're at the locked rotor condition, again, F sub r is equal to F sub E. So let's just look at the equivalent circuit for the rotor side of the induction motor. The rotor equivalent circuit. We have a voltage, E sub r, and then we have an inductor and a resistor. This is JXR, and this is RR, and we'll have a current IR that flows in the circuit. Now the rotor resistance is constant. It's not a function of the frequency of E sub r. However, the reactance depends on the inductance of the rotor and the frequency of the voltage and current in the rotor. Okay, so that's why we said that the inductance, while it was, or the inductive reactance was constant in the transformer model, it's not going to be constant in the rotor model because the frequency in the rotor is not constant. If we consider that the rotor inductance is L sub r, then x sub r would be equal to omega r LR, or 2 pi f sub r L sub r. And we've already said that f sub r is equal to the slip times the electrical frequency. We can rewrite x sub r equal to 2 pi s f sub e L sub r. So all I've done here is I've substituted in the expression SFE in for FR. And this is equal to S, just going to rearrange the terms here, times the quantity 2 pi F sub E L sub r. And if we look at this term in the parentheses, this would be the reactance of the rotor when the rotor isn't turning, the block rotor reactance. That is the reactance of the rotor when the frequency in the rotor is equal to F sub E. So we will call this the blocked rotor reactance, X R naught. So this equals S X R naught. So now we can go back and solve the equivalent circuit. We want to write an expression for I sub r. Let's just look at the circuit again real quick. The circuit's up here. We're going to write an expression for I sub r. Okay, this is a simple series circuit, so we want to write an expression for the current. I sub r is equal to the voltage, E sub r, divided by R sub r plus J X sub r. And I can rewrite this as E sub r divided by R sub r, and now I'm going to use that new term that I just derived, Jx R naught times S times the slip, and this is equal to ER naught. So now I'm substituting in ER naught here, and what does that do? Well, ER naught is equal to S, or ER is equal to SER naught up here. So in effect, I've multiplied the numerator by S, so I have to multiply the denominator by S. When I do this, I get, or I've divided the numerator by S, so I have to divide the denominator by S. So I get RR over S plus J XR. Okay, here I have ER equal to S ER naught. So if I want to write ER naught in the numerator, well, it's just, I need to divide by S, and then I need to do the same thing in the denominator. So what is this getting us? Well, the point here is that the rotor effects that result from the varying speed, or the relative velocity between the rotor and the stator, can be modeled as a varying impedance with a constant source, ER naught. So instead of making the voltage frequency change, I'm modeling it as a varying impedance with a constant supply. So now the equivalent circuit is going to look like this. I have ER naught this is JXR naught. This is R sub R over S, where S is the slip. And here is my new equivalent rotor circuit. Of course, IR flowing in that direction. We can look at the rotor current as a function of the motor speed. If this axis is the percent of synchronous speed that the rotor is turning, and our current is on this axis, then we will see something like this. And this is rotor current as a function of motor speed. Okay, now to complete our equivalent circuit, we've done this analysis on the rotor side. Now let's refer that rotor side to the stator side. So, just as a quick refresher, the voltage on the primary, Vs prime equals A Vs, where A is the turns ratio. So that's a relationship between the primary side and the secondary side current or voltage in a transformer. And we're talking about a transformer here because, remember, if we go back to our equivalent circuit, we have a transformer here, and we want to get rid of that. And the way to get rid of it is to refer these circuit elements over to the other side using the equations for a transformer that are a function of the turns ratio A. The current on the primary side equal to Is prime is equal to the current on the secondary side divided by A, and then a secondary impedance referred over to the primary side, Zs prime, would be equal to A squared Zs. Here the prime indicates that the value is referred over to the primary side, from the secondary side to the primary side. Okay, so if the effective turns ratio is A effective, then the rotor voltage transformed over to the other side the rotor voltage referred to the stator side which we'll call E, which will be equal to ER prime, ER referred over, is equal to A effective times ER 0, ER naught. So we're using these values and referring them over to the stator side. So that's why it's ER naught. The rotor current IR is equal to the IR prime, the referred rotor current, is equal to IR divided by the effective turns ratio, and the rotor impedance ZR prime is equal to the effective turns ratio squared times R sub R over S plus J x R naught. And now we can draw the final equivalent circuit. Note that R2 is equal to the effective turns ratio squared times R sub R, and X2 is equal to the effective turns ratio squared times XR naught.